All right, we have one more presentation before lunch. It's my pleasure to introduce Team Verdigree.
Every year, 400,000 lumbar punctures are performed in the United States, a procedure done by physicians to obtain cerebrospinal fluid for diagnostics. However, 28% of lumbar punctures performed without imaging fail, meaning that no fluid is obtained despite the pain, discomfort, and anxiety inflicted on patients. Furthermore, 8% result in traumatic taps, a complication that involves internal bleeding, which not only adds physiological harm, but $250 million in costs to the patients in the US alone. The target patient population for lumbar punctures is those with a suspected neurological condition. Typically, they're performed by emergency physicians, but they rely on blind guess and check methods that often require multiple attempts to get the correct angle of insertion. Other methods exist, but they don't guide the angle. They can add time and personnel to the operation. There's a need for something that's accurate, has an intuitive interface, low user burden, and integrates well into the workflow, with quantifications from literature and interviews. We need to find a solution that can guide the angle without adding time or personnel to the operation so that physicians can get it right on the first try. That's why we created Verdigree, an ultrasound-based needle angle guidance device for the lumbar puncture procedure. To use Verdigree, the physician will first locate the L3 to L4 space in the spine. Then, with the click of a button, they'll initiate an ultrasound sweep, which consists of generating a wave out, processing the echo back in, and then using our machine learning model to detect the best angle of insertion. Then the physician will attach the needle to the device and rotate until the LED turns green, meaning that they can insert the needle.
Now, how do we actually do this? We'll start with our electronics. So in order to generate our wave, this is what we'll focus on here in our electronics component. We need to excite a 5 megahertz piezoelectric crystal. And then we need to isolate the echo that comes back bouncing off of different materials and process them in our software and hardware. So for this, we rely on the pulse echo principle. That's the idea that with each ultrasound pulse we send out, it will bounce off of different layers of material that have different acoustic moduli. So in our case, we care about the fact that bone has a very different acoustic modulus from flesh or other soft tissue. And so once we know when we receive that echo, we can use the time interval between our excitation and our echo to generate an image, or in our case, we really care about that distance that the image is a proxy for. And so doing this in circuitry means we are generating or inputting a 1 millisecond 5-volt pulse, amplifying that to 100 volts and cutting it down to 200 nanoseconds in order to excite the piezoelectric. And then we receive the echo from that ultrasound pulse, which is around 80 millivolts, and then we amplify it to a maximum of 5 volts so that our microcontroller unit can process it, and then we also filter it to focus on that 5 megahertz signal that was originally sent out. And so throughout the course of this semester, we were able to achieve our goals by first building independent units through our proof of concept. And then in our minimally viable product, we integrated our excitation with the actual probe, the ultrasound probe itself, and a microcontroller unit. And then finally, we integrated with analog processing and top of PCBs so that we could keep everything quite compact.
For our encasing, we started by testing simple electronical components and modeling our CAD in software. Sorry. Could you go back? Right. And then we integrated these sensors with a minimum shell for our MVP, and then had our final enclosure fully CADed and integrated with all our sensors and actuators for our final product. resulting in a device that looks like this. Now, Verdigris begins with a click of a button, which initiates the mode switching and transducer servo mechanism, which are in charge for the transducer sweep. Once that is complete, you can insert the needle into the press fit mount and then view needle insertion angles on the RGB LED. This visual feedback is provided with a latency of 9,600 Hz with an error of less than 1 degree as validated on a low, ideal, and a high target. And for our validation studies, we started by testing our device on simple gelatin blocks for our POC, and then we integrated that with a small Fox spine model for our MVP. And for our final product, we had an anatomically accurate PLA model. Now, before developing our model, we wanted to validate the acoustic properties of all our materials. And we use a commercially available transducer calibrated on a block of aluminum. We then measured this acoustic property of our model phantom gel, and we found it to be acoustically similar to that of subcutaneous tissue, muscle, and collagen, all of which are significantly less than PLA and bone. And for our model itself, we used an opaque layer of the phantom gel on top with translucent layers below it so that we could easily visualize successful needle insertions. And for the bones themselves, we used anatomically relevant models of the lumbar vertebrae and placed them in physiologically relevant positions. And using these models, we were able to verify our accuracy of Verdigris of 80%, which met our goal that we set from the beginning.
For the software side, we started by collecting data using Verdigris on the PLA model that we talked about. We charted out a graph for the angles versus the distance of the echo measured at that particular angle. The farthest distance measured at any angle is considered the point where we need to insert the needle. Here we can see that at around 90 degrees is the optimal angle for needle insertion. To relate this to anatomically accurate data, we collected ultrasound scans using a commercial probe on human volunteers. On these scans, you can see that the skin surface is at the top of the image and the deeper tissues are at the bottom of the image. The brightest region in this image corresponds to the bone edge, which reflects all the ultrasound waves, whereas the bone mass does not have any ultrasound waves passing through it, so it appears black. Our software machine learning model generates masks for bone in red, whereas for soft tissue where we can safely insert the needle, we create green masks. To quantify this data, we created a confusion matrix for the 3 different classes we trained our machine learning model on. They correspond to bone, soft tissue, and background noise. Based on this confusion matrix, we claim that our model achieves an accuracy of 95% for detecting bone and 96% for detecting soft tissue. Hence, we achieved our set accuracy of 95% for differentiating between different tissue types. For proof of concept, we had trained and tested on the Fox spine phantom. For our MVP, we had trained and tested on the human data. And for the final product, we are testing on the Verdigris data and deployed the algorithm onto the PCB.
While we've made substantial progress throughout the year, there are still some future challenges that need to be addressed. First, there are some limitations to our data set. We're working with a limited sample size and a limited population diversity. So we're not including obese patients or patients with spinal abnormalities. In the future, we hope to expand our data set to include a greater sample size and include these populations. Next, we would like to validate our system a bit more. Currently, we've been testing in controlled environments, and in the future, we plan to do more clinical trials to be able to get more user feedback to continue iterating on our device. Another future challenge we hope to address is by integrating our machine learning on board. Right now, this is an off-board component of our device because of our power limitations and compute limitations. But we hope to integrate this into the future with additional features such as extra sensing modalities and a more robust user interface. And as we continue to work on this, we always strive to reduce the error in our system. Currently, we have some signal noise, and we hope to do more enhanced signal processing to reduce that in the future. But overall, we're really excited to introduce Verdigris for an ultrasound-based needle guidance device for lumbar punctures. And with that, we'd like to thank all of our mentors for all of their help and support, and before we move on to Q&A. So with that, we can open the floor for any questions. Thank you.
Great job, guys. Two really quick questions. One, on TV, I see people on lumbar punctures, they're like laying on their sides, and then I saw an image of someone sort of laid, like hunched over. Is there a specific or ideal position for the patient to be in for this to work? And does it require the doctor to be holding the machine at the same time? Is my first question, and then I have a quick follow-up.
Yeah, so there isn't one set position. Doctors prefer if their patients are hunched over, which will bend the spine open, so the vertebrae angles are more generous for needle insertion.
And then, other than angle, is there any other things that can go wrong, like not going deep enough or the needle going too deep, and have you accounted for that?
Yes, 100% those are things that can go wrong. For our particular device, we focused on needle angle as a first goal, especially because from the physicians we talked to, they really stressed getting the angle wrong on the first try as a primary setback, with one physician even citing that he gets it wrong 50% of the time.
Have you guys thought about how you can help the physician get to the right interspace? One of the things that I've experienced, I'm a neurologist, so I've actually done this myself. One of the things I've experienced with other providers is that they don't always get the interspace that they want. And so for this figure that you have here, you're going for the L3, L4, which I actually usually use L4, L5. So does that make a difference? And there are times, because of body habitus or otherwise, where you don't even know what level you're at. And that can be kind of scary, because if you go too high, then you're going to hit the spinal cord, and that's very, very bad. So is there something you guys are thinking about for how to help the physician place the device in the right place from the beginning?
In terms of placing the device, we first, for our primary goal, we relied on the palpation of the surgeon onto the patient's back. But in future iterations, once we collect more data, patient data, hopefully our data set is big enough to account for different vertebrae and how they kind of look and how they differ. So once we have that data, hopefully our model will be able to differentiate between them and help identify where the needle should be inserted.
Yeah, very cool. Interesting thoughts from your project for sure. So one thing, like from a procedural standpoint, is this is a sterile procedure. So usually I prep the skin and then I have sterile surgical gloves on, and I cannot touch anything that's, not sterile. So have you put some consideration into how to maintain sterility when you're placing a device on the skin? Like, is this going to be reusable? Is this going to have components that are going to be sterilized and then discarded? Yeah, I'm just curious your thoughts.
Yeah, that's a great question. And one of the problems with 3D printing, which is the method we use to fabricate our device, is that it comes in infill layers, which is not sterile. So in the future, we'd like to look into better manufacturing practices to produce a main body that is sterile, and most of the components should not be replaceable over time. We would like it to be a one-time or like forever use case device.
Sorry, I'm like blasting you guys with questions. The other question is, your competitor is a physician with a ultrasound machine generating an image, right? So I can go on any ICU, get an ultrasound, put it on the patient, localize where I want to go, make my decision, and then that can all be done under sterile condition. You can take them to IR and do X-ray as well, but that's besides the point. So I guess, with that in mind, like, what argument could you make to say why I should use this device instead of grabbing a full-fledged ultrasound machine?
Sorry about that. Is this easier to hear? Okay, awesome. Our rationale is that for a physician to take an ultrasound, they do have to, from our understanding, need to be able to interpret those ultrasound images. And so by strictly focusing on the angle as like a primary pain point, and then also communicating that information of most viable path where there isn't bone obstruction to the physician via an LED, we aim to take away that overhead of having to interpret the image. And we find that that whole process of just figuring out what the ideal path is will take around 40 seconds from us just going through the procedure on our model.
Great work. Thank you, Team Verdigris.